of the ocean with antimatter. So when we have photons interacting with electrons for our photoelectric effect and our salt plates, we can actually get a number of different interactions to occur. The first interaction we can have is that a photon, which we'll use the gamma symbol for that. Yes, I know, we just talked about how gamma is the Lorentz transform value, but we also use gammas to represent photons. But if a photon hits an electron, and the electron jumps out completely from whatever substance it was in, it is free. We call this photoionization. We've ionized that molecule with a photon. And if you remember anything from your chemistry courses, when you ionize something, it now has some net charge, and that's because you got rid of that electron. Okay? That's photoionization. If that photon hits the electron, and the electron doesn't escape, but it becomes excited, it gains some energy, then it could jump up an energy level to a new excited state. We are going to have a future video on this where we go way in depth about all the interesting things that happen when you excite electrons. But that's the second thing that could occur. The third thing that could happen here is the photon can hit the electron, but it's really going to undergo inelastic scattering, which means it kind of deflects off the electron. We call this Compton scattering. The photon, that light, it's still going to move at the speed of light, but it is going to have a wavelength shift. The wavelength is going to change. We won't need this for the AP Physics 2 class, but if you wanted the equation for Compton scattering, it would be lambda 2 minus lambda 1, where 2 is the scattered wavelength and 1 is the incoming wavelength. This equals h over mc multiplied by 1 minus the cosine of theta, where that theta is the scattering angle. We don't need that for the AP Physics 2 class, but I thought I'd share that with you just in case you ever did. That's Compton scattering, okay? It is widely useful in the world of radiobiology, but this is not a radiobiology course, so we are going to just backpedal slightly from Compton scattering. The fourth thing that we could do here in terms of a photon interacting with some electron here is that the photon isn't really going to interact with the electron. What's going to happen is a photon is going to have so much energy that its interaction with a particle is really going to do the following. It is going to turn the photon into an electron. That's right, light, which doesn't have mass, turns into something that does. And that's totally allowed, because remember Einstein, E equals mc squared. Or more formally, E squared equals the quantity mc squared squared plus pc squared. Or the quantity of that. Okay? So we can do that. We can take energy, light, and turn it into mass. But there's an issue here. Charge is a conservative substance. You must conserve charge in the same way that you conserve mass energy. So if we generate a negative charge into an existence, we also have to generate an equal but opposite charge. We need to generate a positive charge here. And you might be thinking, oh, well, if that's an electron, we'll just generate a proton. That's not what happens here. What we actually generate is a positive electron. This is known as a positron. And it is antimatter. It is anti, the opposite, of matter. It's the opposite of that charge. So this only happens at extremely high energies. And we're going to see in our next video a little example where we actually calculate how much energy do we need for this photon of light to create antimatter, and just what kind of light or what wavelength would that be in order to do this. But for right now, these are the 4 ways that we can have photon interactions. We can photoionize something. We can just excite an energy level, which we'll see in a future video. We can have Compton scattering effects, or we can have pair production, our matter-antimatter setups. But for now, this is finished. Until next time, adios, and take it easy.